So yesterday's problems were a mix of Andrei Stankiewicz contest number 37. It's one I did a long time ago and also wrote an editorial for it, so I don't need to explain everything today because it's explained in more detail, probably even better at Codeforces. I'll give you a link afterwards. And they were padded with some problems from City Open 2012. There are three problems from the contest which seemed nice enough to me. Just no geometry and no nasty implementation problems. Because these problems from City Open seemed easier and those from Andrei Stankiewicz contest were all hard. As it usually is with those contests. So let's just start with the problems from City Open. The first problem from there was ants. It was that we have a line, an x-axis on which there are ants. Each ant is a point which starts at some coordinate on this axis. So x1 up to xn. Each ant moves with the same constant velocity of, I think it was 1 unit of distance per 1 unit of time in some direction. For each ant we are given the initial direction. For example, like this. And what we want to find out is when the last ant drops from this, okay, it's not an x-axis, it's just a segment of this axis with length L, usually between 0 and L. And we want to find out when the last ant drops from this segment and which ant it will be out of the initial ants. It's possible that there will be two ants dropping at the same time, and in that case we should find the indices of both those ants. So for the first thing to notice is that since also there is a condition that when two ants meet each other, for example, these two move in these directions, at this point they meet each other, and when they meet each other then both those ants change direction and start moving in the opposite one. Of course, it can be easily proved that all ants eventually drop from this segment because either the last ant will move in this direction or it will move in this direction, so it will either collide with some ant and reverse direction and start moving here and eventually drop down, or it will, or just all the ants are moving in this direction, so the first one will drop down. So this gives us one less ants on the segment, and if we repeat this then by induction we know that all ants drop. Another thing to notice is that since the ants always reverse directions when they collide, then their order will never change. That also means that the ants that drop from the left end of the wood will be the first several ants, for example ant 1 up to ant k, and the ants that drop from the right and the remaining suffix of the initial ants. x1 through k. It's possible that k equals 0, in which case all ants would just drop from the right end, drop down from the left, and ants k plus 1 up to n will eventually go to the right and drop down from the right. From this we can see that the last ant that drops from the left is ant k, and the last ant that drops from the right is ant k plus 1. That's why there are at most two ants that drop at the same time. we still need to find out when ant k drops from the left and when ant k plus 1 drops from the right, and also what is the value of k. And for this we can use a very nice trick that instead of considering the collisions of ants to be that when two ants collide then they start moving in opposite directions, then we can just say that the ants don't collide. Because if they were indistinguishable, then the number k would still be the same, because it's just the number of ants and not it has nothing to do with their indices. And the time when ant k drops from the left is the same, because it's just the time. Also, it has nothing to do with their indices, and the same for the time when ant k plus 1 drops from the right. If we assume that the ants don't collide but they just pass each other without any effect, then the number of ants that drop from the left and the number of obvious is the same that were moving from the left, moving to the left or moving to the right initially, because when they collide or when they just pass each other is the same. The number of ants that are moving to the left always remains the same, and the number of ants that are moving to the right also always remains the same. And whenever there was an ant moving to the left, then it has to drop down from the left end. It cannot drop from the right end, and when there is an ant moving to the right, it can only drop from the right end. From the right end. K is the number of ants moving to the left initially. The time when the last ant drops from the left is also easy to compute, because we just take the last ant that moves to the left, and maybe the index of this ant, of this last ant that moves to the left, will change during all those calls, but it doesn't matter. If we just want the time, then there is always one last ant moving to the left that at time, if ant n was moving to the left initially, then the position of the last ant that moves to the left, whatever the index of this ant is at time t equal to xn minus t. So if the left end of the wood is at position 0, then the time when the position of the last ant that moves to the left becomes 0, so that ant drops down, is equal to xn. Time when xk drops is equal to x of the last ant that moves to the left. And the time when ant xk plus 1 drops is equal to x of the first ant moving to the right. It's equal to L minus x of the first ant moving to the right. For example, here it would be ant x2 is a symmetric argument that is like we had just the first ant that moves to the right that never collides with any ant. So there is always the first ant that moves to the right, and at time t has coordinate. In this case, it would be x2 plus t, and we are looking for the time when this is equal to L. So using this series of indirect and seemingly contradicting assumptions about the ants, that we are combining a situation where the ants always collide with each other, so their positions, their order never changes. And on the other hand, we also use an assumption that the ants never collide with each other. So, and the time and all those things that are independent on the AND indices are computed using one of those assumptions, and the actual indices are computed using the other. Of course, the time complexity of this is O(n), since we just find the first AND that moves to the left, find the last AND that moves to the right, and then we know the index of each of these ANDs and can find the time. So this was a pretty nice tricky problem. Using these reflections as just passing through is a trick that's used in more problems. For example, some that have a room with mirrors. When you have a room and each side of this room is a mirror, and you want to find out how a ray moves. When you shoot a ray to some mirror, it reflects, for example, like this. Then instead of watching how the ray reflects, you could just reflect the room. And instead of assuming that the ray reflects, just let it pass through a reflection of the room, and so on. And like this you would find out, for example, the number of reflections up to some distance the ray travels. Or, for example, there could be some person in the room, and find out if the ray hits this person if you reflect also that person, and so on. So it's a pretty commonly used trick in any problems in which there are reflections or collisions or something like that. The next problem from that contest I used was software bugs. You can notice that the topic of this contest was about bugs. The topics of some contests are also bugs in official solutions or tests. So software bugs was about having some initial string as 1 to n, and there is a bug string b, let's call it 1 to m, and what you want to do is repeat the following operation. You find the first occurrence of this bug string of b in S, then you remove this bug string, of course occurrence as a substring, not as a subsequence. You remove this first occurrence, this substring from S, and then you repeat it. Take the remaining string, find the first occurrence in that string, etc. So, for example, if you have some kind of ABC is S and ABC is B, then you would find the first occurrence of ABC in here, which is this, remove it, and you would be left with ABC, which is again an occurrence of B. So finding the first occurrence would give you this whole string, you remove it, and are left with an empty string. you can see that it isn't so simple to find out how those occurrences of the string exist, because you can concatenate two remaining parts, and after you delete some occurrence of the backstring, and then another occurrence of the backstring appears. But this is a very standard problem for KMP. KMP is basically about always keeping some state in some. You add the characters of a string S one by one, and you remember a state which is the longest prefix of the string B, which occurs at the current position in what you currently added from S. So when we had this string AB, ABC, then it's added one by one, so we have A. Then we know that the prefix of the backstring ABC is equal to A. So the length of this prefix of, when we add, we start with an empty string, then we add this first character of S. This is A. We can see that the length of the prefix of length of the longest prefix of B, which is a suffix of currently added part of S, is 1, because this suffix is equal to the whole string A, and it's this prefix. Then we add B, so we know that the length of the prefix is 2, because it's AB. Then we add A, and now the longest prefix of B, that's a suffix of this string ABA, is just A. BA or ABA aren't prefixes of ABC, so this is just A. The length of it is 1. Then we add B, and again we have length of the prefix of B equal to 2. Then we add C, and now we can see that the length of the longest prefix, so we have already found the whole backstring over here. And what we need to do now is remove these last M characters from what we currently added. So ABC is deleted. And the advantage of this approach is that we just go back to some state which we already processed. So a state in which we have the longest prefix equal to 2, and then we add this last character of S, which is C, and then we again see that the longest prefix of B, which is also a suffix of S, is the whole string B. So again we remove these last M characters and go back to the state which is the empty string, and we have processed already all characters from S, so we're done. KMP is a fairly well-known, well-described algorithm, so I won't describe exactly how to find out and why we can find those prefixes of B that are suffixes of the currently added, well, what remains from S after removing backs so far. It's just good to know that we can always find those lengths of the longest prefix. Let's say that we have some that when we have so far added some characters from the start of S and removed some bugs in the process, like I just described, that we have some string R, and we want to know the length of R, which is the longest prefix of B, that's a suffix the length of the longest such prefix of B, that's a suffix of this currently created string R. And we always either add the next character from S, so L R plus SI can be computed in time that's not necessarily constant, but always amortized constant. So in the total algorithm, the time complexity is linear in n plus m. So it's possible to compute all these longest prefix suffixes whenever we have some state, some string that's created from S. Then after adding some character, we can always compute the next length of this longest prefix suffix. And then if this is equal to m, then we throw away the last m characters from R, and we get the state which corresponds to what we to some prefix of this string R, which is a state which we already processed. Go back to an older string R. Actually, in this problem, m was up to 1000, so it was even easier to pre-compute some. What we pre-compute in KMP are for each prefix of B, the next prefix of B that ends at the same position. So, for example, if we had B equal to AB, AB, then for, or AB, ABC, then for the prefix AB, AB, this, what we'll pre-compute that the longest prefix which ends at this position is has length 2, so this is prefix AB, because AB is a suffix of this whole string, and using these numbers, which can be computed in linear time, it's also a part of the KMP algorithm, how to compute them, and in this case we could just afford to compute them by brute force. So we just do a standard KMP algorithm. If whoever doesn't know it can just look it up, because it's completely the standard algorithm, but just with the difference that whenever we reach this length of the longest prefix suffix equal to m, it can never be longer than m, because whenever we reach it equal to m, then we jump to some previous state in R in which it has some shorter length. So yeah, when we see that it's equal to m, we remember that the last m character should be discarded and go back to some older state of R. And what we want to find out is the resulting string R after removing all bugs, after removing all occurrences of the bug string one by one. So this is just the string R that we get at the end when we finish adding all characters of S one by one. So this is in O(n) plus m. The third problem from this City Open contest was about finding some MST. Somewhat special MST because, okay, I think we aren't told explicitly that it should be an MST, just a subgraph which is connected and has some cost. So we have a graph with n vertices, m edges, let's say like this, and each edge has some length, and we want to find the cost of the minimum cost of a subgraph which is connected. So, for example, we would choose a connected subgraph by these edges. So we would just discard this edge. And the cost of such a subgraph is the sum of lengths of its edges minus 2 times the maximum length of an edge. Unlike with the minimum spanning tree, in which we are trying to find just the minimum sum of lengths of edges, in this case we want to take all. Okay, if this was a spanning tree, then we would take the sum of lengths of edges except the longest one, and then subtract the length of the longest edge. So instead of writing a sum where it's except the longest one, I just subtracted the longest edge twice instead of once. So this is the cost of a graph with, of a subgraph with some edges. It can be easily proved that this has to be a spanning tree. So it has exactly n minus 1 edges, because if it had at least n minus 2 edges, and if it had at least n plus 1 edges, then it would have a cycle which doesn't contain the chosen longest edge. If there are multiple longest edges, we can just choose one of them. There's no problem with that. So the edge, there would be one edge which is in this sum and isn't subtracted, and we can just discard it since it's on a cycle, and if we discarded it, this sum would decrease. Since this sum would decrease, this sum would stay the same, and the graph would stay connected. So there are definitely at most n edges, and if there are exactly n edges, then there is exactly one cycle. This cycle has to contain at least 2 edges, and we can repeat the same argument, because one of those at least 2 edges on the cycle has to be different from this edge which we subtract. So the longest edge, we could just remove one edge from the cycle such that it isn't the longest edge, so this term in the sum doesn't change, and this sum decreases, and the graph stays connected since the edge was on the cycle. So there are exactly n minus 1 edges, in the subgraph we want. For example, we wouldn't use this edge, this would be a valid subgraph. And now we want to find out what's the minimum cost of this. There aren't any simple greedy solutions that will work, but we can notice that if, for example, this is the longest edge, so this is some edge with length L max, and this is, for example, an edge with length 1. This is also an edge with length 1. Then let's say that we found the minimum spanning tree of the original graph, just ignoring this term, just a minimum spanning, whichever one of them works. That spanning tree, in this case, if Lm is some large number and these two edges have lengths 1 and 1, then the optimal minimum spanning tree would not use this edge and it would use these two edges. And now we can try adding any edge out of those remaining ones. Of course, there's the possibility that the optimum is just this minimum spanning tree. If, for example, the original graph is a tree. So we can. So first we should check what's the value of this cost for the minimum spanning tree, and then try replacing one edge in the spanning tree by each one of these edges that aren't used in the spanning tree. So for example, this edge and this edge. So, e.g. for this edge, we could say that we want this edge. Now there is one cycle since we added this edge to the original minimum spanning tree, and it's not hard to prove that when this edge is added, we don't. What we want to do with this graph with n edges in total is never to add some other edges from the original graph and remove more edges from the spanning tree, but just to remove one edge from the spanning tree. And of course, the edge we want to remove has to lie on the cycle which is created. We just added one edge to a spanning tree, so we created exactly one cycle. It was a tree, so it's easy to know which cycle it was. If we added an edge between vertices u and v, then in the minimum spanning tree it would be the cycle formed by this added edge and the path between vertices u and v. There are some nice tree algorithms to handle paths, but in this case we'll see that what we need is quite simple. So for example, if these two edges would have lengths 1 and 2, and this edge which we would want to add has length 3, then which edge should we remove from this cycle? Of course, it's the longest one, since we are adding an edge which is longest. This cycle has greater, if the longest edge at this cycle is longer at this path between u and v, or in the original MST has length greater or equal to the length of this added edge, then we shouldn't add this edge at all because it doesn't benefit us in any way. So we just find the longest edge in this out of this path, and instead of having just this sum of edges in the MST, we subtract from that sum the length of the longest edge, and then subtract the length of this edge. So instead of having the sum of lengths of these both edges, this longest edge on this path, this gives us the sum of lengths of n minus 2 edges, which is this in the resulting cost of the graph. It would be this sum of lengths minus 1 times the maximum. If it was the optimal spanning tree in the end, and then we again subtract the length of this edge because it's minus the new maximum. So what we want is to maximize the sum of lengths of this edge which we add, and the length of the edge which from this path which we remove. Of course, we can just try all possible edges to add, and then for each of them we need to find what's the length of the longest edge on the path between the vertices this added edge connects. We still haven't described how to do that, because it runs in, so far if we just did that by brute force, by some DFS or something, then it would be an O and M algorithm by brute force. But we can find this length of the longest edge on any path in the tree in O n log n time. So O n log n, we want to have this MST. This is found at the end. It's a fixed tree, which is the same for all edges. So for example, a tree like this, let's root it at some vertex, for example vertex 1, it doesn't matter at all. And now for example we want to find the length of the longest edge between this vertex and this vertex, so on this shortest path. And this can be done by some LCA-like algorithms. When we are finding the lowest common ancestor, then for each vertex we want to find its parent when we go up one edge, parent when we go up 2 edges, 4 edges, 8 edges, etc. And then we can find its parent when we go up any number of edges just by representing that number of edges in the binary. And then just using those jumps which we pre-computed. There are O n log n of such jumps, and we only need O log n of those for going any number of vertices, any number of edges up. And in this case we can do a very similar thing. We also pre-compute what's the number of edges we need to go up. When we also need to find out what's the LCA of these two vertices. Since then we just go a required number of edges up. So we would get from one of the endpoints of this path to the LCA, from the other endpoint of this path to the LCA, and for each of those paths, each of them goes just up. So it will be easier to compute the maximum length of an edge on such an upward path, and then we just take the maximum of these. So instead of having a full path, we just find the LCA of this vertex and this vertex, which is this one, the lowest common ancestor, and then we just take the maximum length on this path and the maximum length on this path. And yeah, when we want to find the lowest common ancestor, we know these ancestors at 2 power k edges up. When we know the depth of all vertices, first of all we just look at what's the depth of the deeper vertex out of these two endpoints. For example, let's call them UV. So the maximum depth of U and V, and then we move 2 power. Then we move dep V minus dep U edges up. So for example, from vertex V here we would get to this vertex. Now this vertex is deeper path. The deeper path got reduced to a path which is with the same depth as the shallower path. So we are starting from 2 vertices that are on the same depth now, and now we can just check, for example, at 2 power, when we jump 2 power 19 vertices up, was the vertex we get to from here, and if they are the same, then the LCA is somewhere, is either that vertex or somewhere below it. So we don't use that jump. If they are different, then we do use that jump, and do the same for 2 power 18, 2 power 17 edges up, and so on. Of course, it's possible that when we went up from this deeper vertex, we just got to the LCA. That's if the shallower vertex is a parent of the deeper vertex. Then, for example, if this was vertex u and this was vertex v, then going one edge up would give us u equal to v. That's a special case which we need to handle. If that happens, we just don't go up. Just know that the LCA is this vertex, is this shallower vertex. So in this case, it would be vertex u. It would be this one. And otherwise, we just try to jump by all powers of 2 from the largest one to the smallest one, up to just jumping one edge up from each of these vertex, so from this vertex and this vertex. And in the end, if these two vertices were different at the beginning, then the resulting pair of vertices which we get is also different, and we know that the LCA is their own parent. The parent of each of these vertices is the LCA. So we just go one edge up again. So how do we use this LCA algorithm for finding the maximum length of an edge on a path? Of course, just like we computed the parent at 2 power k edges, or ancestor at 2 power k edges up, we can compute the maximum length of the path from any vertex 2 power k edges up. So for example, for 2 power 1 edges up from this vertex v, we would compute the maximum of lengths of this edge and this edge, just on the path between a vertex and its 2 power kth ancestor. This can be done in a very similar way to how we compute this. These 2 power kth ancestors, just instead of moving, when we compute the k ancestor of v is obtained by taking the 2 power k minus 1 ancestor of v, and then 2 power k minus 1 ancestor of if this 2 power k minus 1 ancestor of v was w, then we just take 2 power k minus 1 ancestor of w. So we move 2 power k edges up by moving 2 power k minus 1 edges up, and then again moving 2 power k minus 1 edges up. That's 2 times 2 power k minus 1, which is 2 power k. And when we want the maximum number of the longest, the length of the longest edge, the maximum length of an edge on this path, then we just take the maximum of the longest edge on this path and the maximum of the longest edge on this path, which we compute recursively. For each k, we can just compute these numbers for each vertex v. And since 2 power k should only be up to n, since there is no point going more than n edges up in a tree with at most n vertices, then k is just up to log n, k is all log n, and for all possible k and all possible n, the time complexity of this, since each number is computed in all one time, and there are all log n times n numbers, then the time complexity is O log n to pre-compute all these parameters. Edge which we add in this original graph, so for each pair of upwards paths in the MST, we just need to spend log n such steps. Again, we just express the length of the path in binary, and whenever there is one when the case bit of this binary is 1, then we just use a jump by 2 power k. It doesn't even matter in which order we do these jumps, because in the end we always count each edge or each jump by 1 edge up one time, and out of these jumps by 2 power k edges, we again take the maximum of lengths of the edges that are on this simpler paths 1, 2, 4, 8, etc. This is actually everything. Finding the MST is an either O log n either something like O m log n or m plus n squared, depending on what sort of data structure we use for it. If we just try brute forcing and out of n optimal edges n times, and don't put the edges in any special data structure, or if we put them in a priority queue, this is somewhat slower for this case, so it's better to find MST in O n plus n squared time, because n is sufficiently small. If n was large, then we would have to use this algorithm. There are many algorithms for finding the minimum spanning tree that are wildly different. They all work in roughly the same time, either this or this. It's good to know how the different various modifications of MST problems that aren't always solvable by any algorithm, but need some specific one, and you need to modify that algorithm in some way. This is finding the MST, and then for each edge we still need O log n time, of course, plus O n log n plus m log n, and since m log n is anyway necessary, then O m log n is the overall time complexity, or O m plus n squared plus or O n squared plus m log n if we wanted to use this algorithm for finding the MST. There is one more thing I wanted to talk about that isn't related to the Andrei Sankiewicz contest problems, and since they have editorials online anyway, then I'll give some time to this topic, which is solving linear recurrences and solving some more complicated linear recurrences. There are some very simple ones, like in general, a linear recurrence with constant coefficients and so-called homogeneous is a sequence, is about computing a sequence by some ck a n minus k, where k goes from 1 to, let's say, m. The ck are constants. You can notice that this is very similar to how we were computing when I was talking on the first day about Fourier transformations and about convolutions. There was one problem. This isn't exactly a simple convolution, but there was one problem or type of problems where we needed to compute such a sequence, and it was doable in O n log squared n time using some divide and conquer approach, and this is basically the same thing, except there it was possibly the coefficients could have been, there could have been much more coefficients, and in here we are interested in recurrences where m is sufficiently small. For example, not m up to m comparable to n, but n could be up to 10 power 18, it could be any long or any very large number, and m is much smaller than n. For example, 2, 3, 10, possibly 100 or something like that. So this kind of recurrence, when m is sufficiently small, when it isn't a massive number, and on the other hand n is a massive number. If we had that problem with the linear, with the convolution, instead of looking at it as a linear recurrence, then there was n up to 10 power 5 or something like that, because we needed FFT or Karatsuba or something like that for solving convolutions of up to n numbers. Here we just want to find out, for example, the value of some an, n for uppercase n, so that I could distinguish it. And in this case, m is very small, and this indicates that we could use some matrix approach, because we don't need to remember many previous terms of the sequence. So for example, if we wanted to compute an, we need to remember an minus 1 and so on up to an minus m. And we could take this to be a vector and do some matrix multiplication using these vectors and some suitable matrices. Since this is linear, in the matrix we would use in this case if we multiply it by an up to an minus m, then we would get n plus 1 up to n plus 1 minus m, and we want to find out what's this matrix. Of course, this is an. For example, the second term would be an plus 1, an minus 1, an minus 2 up to an plus 1 minus m. And these terms already exist in this vector. There is one good way to remember how to multiply matrices, that we take this vector, rotate it by 90 degrees, put it on the top row of this matrix, and try to compute the sum of first element of this vector and the first element of this matrix, the second element of this vector and the second element of this first row of the matrix, and so on. So if this was XYZW, then we would take times x plus n minus 1 times y plus n minus 2 times z, and so on. And this sum would give us the first term of this top element. Let's leave the top element for later because it's computed by this recurrence. Let's just say that we want to find the bottom row of the matrix, because when the bottom matrix is multiplied by this vector rotated by 90 degrees, then we get an plus 1 minus m. An plus 1 minus m is the second to last element of this vector. So we just use 1 as the second to last number in the bottom row. 0 and plus zeros everywhere else. So if we multiply this vector by or this row of the matrix by this vector, then we just get 0 times an plus etc plus 0 times an plus 2 minus m plus 1 times an plus 1 minus m plus 0 times an plus m. So this is an plus 1 minus m. Since here the previous element of the resulting vector would be an plus 2 minus m, is the third element from the bottom of this vector. So in the second to last row of the matrix, we just want the third element from the end of this row to be 1, and the rest can be 0. So for example, this diagonal is full of 1s, the rest in these rows are zeros, and we are left with just the top row. How to compute the top row? Well, we want an plus 1, which is an times c1 plus an minus 1 times c2 plus and so on. So an times c1, this is c2 up to cm. So an plus 1 equals an times c1 plus n minus 1 times c2 plus an minus 3 times c3, and so on up to an minus m times cm, just like in this formula. This is pretty simple, not hard to figure out. We can denote this matrix by m. It's an m times m matrix. As I mentioned, m is small. For example, here we had m equal to 5. Uppercase m. Let's denote this matrix by uppercase the vectors we are computing by Vn. So m times Vn equals Vn plus 1. Since this multiplication of matrices and vectors, or if we consider a vector to be just a matrix with only one column, then multiplication of matrices is not commutative. We cannot just swap these terms in any way, but it's associative. It doesn't matter in which order. If, for example, we had m times n times m times, for example, r times Vn, then it doesn't matter if we first multiply matrix m and matrix r and then multiply the resulting matrix with vector Vn, or if we just compute r times Vn and then multiply it by m from the left. It's the same if we compute this or this. Of course, the result is the same, but the time complexity can be wildly different. If we first multiply two matrices, the multiplication of two matrices is in O m to the power of 3, and the multiplication of a matrix and a vector is just O to m to the power of 2. M times M matrix, this was an M times M matrix, and this was an M times 1 matrix, or just vector of length M, then this would be OM to the power of 3, and this would be OM to the power of 2, because first we just do this. This can be computed OM to the power of 2, and we get a vector. The product of a matrix and the vector is again a vector. So we get a vector with again size M, and we again multiply it with a matrix of size M times M. So there are just two multiplications of a matrix and a vector, which is much faster. It's useful in some problems, and in other ones it's impossible to avoid it. For example, there's exactly this problem of finding AN. Since AN is just the top element of Vn, then we can find the vector Vn and then take the top element of this. And Vn is equal to, since matrix multiplication is associative, this is equal to m to the power of n times V0, where V0 is just given by some initial conditions. Is most likely going to be a vector with some m elements given on the input, or possibly just 1, 0, 0, 0, 0. And it doesn't really matter what's this vector, because there is just one multiplication by it. It's not expensive. The problem is computing m to the power of n. Since n can be up to 10 power 18, we of course cannot just multiply by this matrix over and over, even though there is m squared time for each multiplication of a vector by a matrix. Then it would be OM squared times n time, which is bad. But we can use this fast exponentiation. Most likely we work modulo some prime or modulo some number, or possibly in real numbers. But in real numbers it's very easy for these numbers to blow up. The exponents would be massive, and it's not a good thing. So we usually work modulo something. And in that case, we could use, instead of multiplying a vector by a matrix, we would multiply matrices. We would just compute this m to the power of n completely without knowing this vector V0. And then we would multiply the resulting matrix by this vector, so m squared for this multiplication, plus log n matrix multiplications. So m to the power of 3 times log n. And since n is so massive, then the logarithm means this is obviously the better choice. And there is no way to avoid multiplying matrices all log n times. By the way, as I mentioned caching yesterday, caching is quite useful in multiplying matrices also. There are some special schemes you can find it. It's called, sometimes it's called blocks with sufficiently small size, such that we always work with blocks that are already in cache and reuse the same numbers in the multiplied matrices very often. I won't describe it here because it's quite complicated as to why it works so well, especially. So this is a simpler recurrence where but we can also work with a recurrence where there is one constant coefficient at the end, or where the coefficients aren't constant but are some polynomials, or something that can be expressed using matrix multiplications in some way. So, for example, let's add some number b at the end of this formula. Nasty in that we can't express it in any way using by modifying this original sum, because this sum always has a term times always has every term multiplied by an element of this sequence, and d isn't multiplied by any element of this sequence, it's multiplied just by 1. So we need some different way to do this, and it's done by extending. Of course, we again want to compute a uppercase n, and it's by the same approach as we used before. We just need different matrices and different vectors. What's done in this case is that instead of taking a vector vn like this, we take an minus 1 etc. an minus n minus m and d. So this will be vn. Instead of having just that vector, we added this number d at the end. The advantage of this is that, this number is constant at the bottom of every vector, so when we extend this matrix M, we would want D here. Again, we would want D here, and we want something more in this matrix. The matrix must have one more row and one more column, since it should be a square matrix. And of course, D is here. Bottom row should just be 1 at the end, and the rest is the same. And now in each row, here again we have zeros, since these rows at the bottom are just copying from this vector to this vector. There's no problem with that. And here in this formula, in this top row which represents this formula, we just add 1 at the end of the row. So when we multiply it, what was there before is the same, and then we just add 1 times d, which is exactly what we had in this formula. There was one problem in, I think it was Topcoder Open round 4, that it was the hardest problem. It was about doing something with, always we have some sequence of numbers. We take the top, the front m numbers, use the formula like this on them, compute the resulting number, or no, we had numbers that were generated by this formula, and then we just sum up the first m numbers and remove them from the sequence, and then move their sum at the end of the sequence, and we do this a fixed number of times and want to know what's in the sequence at the end. So I didn't realize, because there was this constant coefficient, and I didn't realize in that problem that I can just use a constant coefficient and express all numbers in that initial sequence as just m to some power, m to the power of 0, m to the power of 1, and so on, and m to the power of length of the initial sequence, and then assume that they are all multiplied by some constant initial vector, which is something that I would only do at the complete end of the algorithm, when I would have what I need. And instead of counting each number exactly, I would just remember that it's some what kind of matrix it is multiplied by that fixed vector. And in that problem, yeah, I didn't realize that I can just add this constant coefficient to the vector, and if I do that, what I needed to do if I had a representation like this was just be able to compute some products of matrices, exponents of matrices, or as I showed, what was it, yesterday or sometime before, when I showed how to compute these sums 1 times m plus m squared plus m to some power of n, that this can be computed in O log n squared times size of m to the power of 3 time. So O log n squared multiplications of matrices. Then this was also part of that topcoder problem. And that problem is quite simple if you know how to do that and know how to express this formula as matrix multiplication, even with the constant coefficient. We could possibly have some more complicated formulas, for example, d plus e times n. If we had that, we would need to add something more to this vector. But again, it would just be this term e times n. Yeah. And 1, or we would just remember n and add a number 1 at the end of the vector, just a constant. And this constant would be so that we could express everything here again using just matrix multiplication. In this case, if we had d times en, then here we would have e and then 0. That would give us plus d times 1 plus e times n plus 0 times 1. And this should be n plus. It wouldn't change, it would be just like this. 1 wouldn't change, just like d doesn't change. And it's simple to just add numbers here at the bottom right end of the matrix in such a way that when we multiply n1 by that submatrix 2 times 2, we get n plus 1, and 1. So even something like that can be done if we augment the vectors in some suitable way. If we had non-constant coefficients, we could keep the coefficients. For example, if ck would be equal to e times k, then we could keep those coefficients as some next terms of this vector, and again we would just if the coefficients aren't constant, it's a more complicated approach, but we could always do some trick. If we have non-constant coefficients, we could take, for example, differences of two expressions, and most coefficients that if coefficients that are linear would just subtract from each other and give us some simpler formulas. If the coefficients aren't polynomial at all, then it's quite a complicated thing to do, and it doesn't really appear in problems, so that shouldn't worry us too much. If that happens, the problem usually has some sufficiently small constraints, or it's solvable in some different tricky way. And there is one more thing I want to mention regarding these regarding expressions like this, that when I talked about power series on the first day, these can be the terms of a power series or the coefficients of a generating function. So if we have some function f x equals sum of a n x to the power of n, where n goes from 0 to infinity, then we can apply this formula and make it a sum of ck a n minus k x to the power of n, where x to the power of n can again be split into x to the power of n minus k and x to the power of k. This is a sum over all n and all k like this, where we assume that a with negative indices are 0, a n minus 1, a n minus 2, and so on are 0. A0 is some initial coefficient, or we are given the initial m terms of this sequence. So if we split the sum like this, we can write it as sum over all k from 1 to m over ck x to the power of k sum of a n minus k x to the power of n minus k, where n minus k goes again from 0, because any smaller indices would give us just terms equal to 0. To infinity, because n goes to infinity. And we can notice that this is again function f. And this is some polynomial, because it doesn't have the sum up to infinity, but only up to m. So it's a polynomial in x, and we can call it px. So we have a formula fx times px minus 1 equals 0. Wait, I forgot something. Alright, this is just a formula for a from n greater or equal to m. It's not exactly like this. N greater or equal to m. So this is a formula over from n equal to m to infinity. It's not fx, but it's fx minus some constant. So this polynomial is still there. Here we have a sum over n greater or equal to m plus sum over a k, where k is 0 up to m minus 1. So this sum can be split into the first m minus 1 terms, and the next terms m up to infinity.
Isn't x power to k?
Here?
Yeah.
Yes, it's here too. X to the power of k. This is a polynomial. This can also be split into this. Okay, this is a polynomial Rx. This is a polynomial Px, and here we have functions like this, which are again some fx minus the polynomial is sum of nx to the power of n, where n goes from m minus k to infinity. So this is fx minus the sum of a nx to the power of n, where n goes from 0 to m minus k minus 1. Since fx is the whole sum from n equals 0 to infinity, then this sum that goes from m minus k to infinity is fx minus this polynomial. It's very similar to this polynomial, so the resulting formula is that fx is px fx plus some polynomial. Let's just denote it by qx. This polynomial q is just this polynomial minus px times some of these polynomials. We can probably express it in some simpler way, since this sum is sufficiently nice, and there is this polynomial p. But anyway, we know that fx is equal to qx divided by 1 minus px. And before, on the first day, I showed that for each polynomial we can express, we can find any coefficient of its inverse. Its inverse is not a polynomial, not necessarily. It can be any function which is expressed by an infinite series like this, and we can find any of its coefficients in sufficiently simple time. So if we wanted to find out what are the coefficients of fx, then we would need to find suitable coefficients. Well, we would need to go through all coefficients of qx and find suitable coefficients of 1 minus px inverted, and multiply these pairs of coefficients, sum them up, and we would get a. This is another way to find terms of this linear recurrence. Probably more complicated, but there are some useful ways to modify this for different problems. Okay, we're approximately at half time, so let's take a break. Let's say 10-12 minutes until 11:20. machine was bubble sort. This is just about having some swaps and well, order of swaps in a permutation. We are given n times n minus 1/2 numbers, which represent the order in which some swaps do or don't happen in a permutation. That's basically the point of that problem. There are some complicated things about bubble sort machine, but it's not important at all because we are just given the swaps, and we just need to know that there are at first n-1 swaps that happen at once, n-2 swaps that happen at most, n-2 swaps that happen at once, and so on up to one swap that happens. N is up to 200. And we want to know if there is a permutation such that this bubble sort machine, when run on this permutation, produces. Of course, since we are given the swaps, since we know the order in which they appear, well, those first n-1, next n-2, and so on, the order isn't given uniquely, but it doesn't matter because they are on disjoint pairs of numbers. So we can just order them in some way and know that there are numbers with indices a1, b1 are swapped, a2, b2 are swapped up to some ak, bk in some initial permutation p1 to n. Then we have pa1, b1, and from this we get pb1 and pa1. So these pairs of numbers are swapped in this order, and we want to know if there is a permutation like this such that the bubble sort machine, when run on this permutation, produces the correctly sorted permutation, so 1, 2, 3 up to n. And if so, what that permutation is. Of course, since the swaps are uniquely given, then the permutation, if the permutation exists, then because we can just find out, we can just start with a permutation p1 to, pi equals I, so the identity permutation, apply these swaps one by one, then we get some new permutation, and we know that whenever we give some, let's say that the new permutation is R, and we know that whenever the initial permutation is P, then the resulting permutation is P combined with R. Let's denote the combination of permutations by this circle, or multiplication of permutations, or whatever it can be called. And we know that this is the identity permutation. And since multiplication of permutations can be inverted, then we know that the initial permutation P must be the inverse permutation of this permutation we got after swaps in the identity permutation. So we just make the swaps, find R, find R inverse, and get a necessary candidate for the resulting permutation. Of course, it's possible that this permutation doesn't produce the given sequence of swaps, so we just need to simulate the bubble sort machine correctly, check which swaps are made, and see if we don't need to even find out how the bubble sort machine works. It's just that whenever we make a swap, it has when we swap PA1 and PB1, then PA1 must be greater than PB1, because the bubble sort machine swaps to numbers when they are in the wrong order. and this would work in ON because the number of swaps is up to this would work in up to ON squared because the number of swaps is up to n squared, or n times n minus 1 half, which is ON squared also. This was a very simple problem. Another problem that's simple but annoying to code is C-port. Which is just about some cargoes of different types that arrive on different days, have different weights, and you have n types of cargo. You have n pieces of cargo. You have m cranes, and each crane has some speed with which it unloads cargo. It has to unload one cargo. It has to continuously unload a cargo from one ship. It cannot skip to some other cargo, and you have some conditions as to how the cargoes and the jobs are distributed among the ships. There isn't basically anything to decide there. Almost everything is given to you. How the unloading works, which cranes unload cargo from which ships, and when they unload it, and for each cargo you just need to simulate this process and find out which crane unloads it in the end, according to these rules. So it's just a problem where you need to and properly take care of how exactly the simulation works. Simulate the process in some efficient way using some suitable data structure. I think the resulting time complexity was something like n log n or m log m. And there isn't much to be said about this problem. It's just implementation using good data structures. One very interesting mathematical problem in this context was a chromatic number. This was about taking a cycle with length n. So, for example, here we would have a cycle with n equals 7 vertices, and now we want to color each vertex with some color. We want the maximum number of colors. We don't want any two vertices that are connected by an edge to have the same color. So this has, for example, colors C1, C2 up to Cn. We want Ci different from Ci plus. So I could use modulo C1 through Cn minus 1, I plus 1 modulo n. And we want these colors to be from, let's say, 0 to A, or 1 through A, C, I are from 1 to A, and each pair of colors X, Y appears at the ends of some edge. So we take all possible pairs of colors. There are A times A minus 1 divided by 2 of them. N minus 1/2 pairs of distinct colors. At the ends of any edge there has to be a pair of distinct colors, and each pair of distinct colors has to appear at the endpoints of at least one edge. We also want this number A to be maximum possible, and the goal is to produce an assignment of colors to vertices, so this sequence C0 up to Cn minus 1, or determine that it isn't possible. And find what's the one sequence with this maximum A, and find out what's this maximum A. So how to solve this? Instead of having colors on some graph, let's say that the colors are the vertices of one graph. So if we knew this number A, then we would have, for example, for this maybe 2. Let's say that A equals 4 for some graph. So for example, we would have a graph of colors with 4 vertices. If A equals 4, then these are colors 1, 2, 3, 4. And we can translate the edges from this cycle to edges in this graph. So if there is an edge between vertices u and v in this cycle, then we can make an edge between vertices cu and cv in this graph. We want it to be at least a complete graph, so this graph, after we translate all edges from this cycle to this resulting graph, it has to be at least a complete graph plus some edges. Of course, there can be multiple edges in this graph. There is no reason why there wouldn't be. And in the end, since we had edges from a cycle, then these edges have to correspond to some Eulerian cycle in this graph. So some root that visits each edge exactly once and returns to the same vertex as it was initially. If we can create a graph which has an Eulerian cycle, which has exactly n edges, of course we need exactly n edges in it, and has this A, then we have one, because we just need to find this Eulerian cycle in a fixed graph. Well, construct such a graph, find one of its Eulerian cycles, and just return that cycle of colors as that sequence of colors in this cycle. So how do we do that? Of course, if it's at least a complete graph, then it's connected. There are two conditions for when a graph has an Eulerian cycle, which are that it's connected and each degree, the degree of each vertex is even. Since the graph is connected, this degree has to be at least 2. And since the degree of each vertex must be even, then there are two different cases. One of them is when A is even, and one of them is since when A is even, then each vertex in a complete graph has to have an odd degree. So we need to add some edges, obviously, and if there is an odd number, if the number A is each vertex has an even degree, so this is satisfied, but we still need to add some edges, possibly to make sure there are exactly n edges. Of course, if a minus 1/2 is the minimum number of edges in the complete graph, so if this is greater than n, then we fail. It's impossible to create n edges because we have more than n edges already if we have a complete graph. This is an obvious case. This gives us some loose bound on A, but we will see that we need some tighter bound to make sure some A is possible. And we need to also find out why it's possible for which A to create a satisfying graph. So let's do this. Again, what we need to do is just take a complete graph which is definitely connected, so this condition is obviously satisfied, and add some edges in such a way that it would have exactly n edges in total, and the degree of each vertex would be even. So this is where A is even, and we will have a case where A is odd. So when the number of colors we need to use and the number of vertices of this complete graph is even. Okay, let's take a complete graph with a vertices. So it has an odd degree. Each vertex has an odd degree of A minus 1. And we need to add some edges so that this would have an even degree, and then possibly add some more edges. Of course, since each edge only fixes the degrees of two vertices, and there is an even number of vertices, then we need to add at least a half edges. It's clear that if we add exactly a half edges between opposite vertices, so vertices 1 and a half plus 1 or 2 and a half plus 2 and so on, in this case between 1 and 3 and 2 and 4, then the degree of each vertex is even, and we have this exact number of added edges. I'll write also a times a minus 1 half, as this is the initial number of edges of the complete graph. So this is a squared half edges. This is obviously the minimum number of edges we need. You can also see that this is the exact number of edges for which, if we have n which is any larger, then we can just add pairs of edges. So, for example, we can add edges between any triple of vertices or any pair of vertices in such a way that each degree remains correct. If let's say that this is MA, and we need to add MA edges. If n minus MA is even, then we just add n minus MA edges between, for example, vertices 1 and A, and this makes sure there are, since this is even, the degree of vertex 1 and degree of vertex A remain even, since we added just this many edges between them, and everything is fine because we had MA plus n minus MA equals n edges, and if n is odd, then we need to add, for example, if n minus MA is odd and greater or equal to 3, so there are 3 cases. Either this number is even, which we just handled, or it is greater or equal to 3, in which case we just add edges between vertices, for example, 1 to 3. This is a cycle. Each vertex gets degree increased by 2, so So all degrees remain even and everything is fine. Again, we just get to the case where n minus the number of edges currently present in this graph is even, and this is the case which we just solved, so it's also possible. And finally, if n minus ma is equal to 1, then n is equal to a squared half plus 1. And while we can't just add one edge because that would give us an odd number of cycles, an odd degree of for some vertex, instead of adding a half edges here, we could add edges in a different way. So instead of this, we are starting with a simple complete graph without any duplicate edges. Of course, the condition that any two vertices connected by an edge in the original cycle have different colors means there are no self loops. So the degrees of all vertices are clearly well defined. So we need, if ma is equal to a squared half plus 1, then we need to add a half plus 1 edges. So we can add an edge between edges between vertices 2 and a half plus 2, 3 and a half plus 3, and so on, and then we are still left with vertices 1 and a half plus 1 having odd degrees, and we still need to add 2 edges because n is this plus 1. We added a half minus 1 edges, so there are 2 left, and these 2 edges can be, for example, 1, 2 and 2 a half plus 1. So this ensures vertex 2 still has an even degree, and since it was a path between vertices 1 and a half plus 1 with length 2, we just added 2 edges and ensured each vertex has the right degree, has an even degree. So we can see that whenever n is greater or equal to a half plus 2, a half divided by 2, then it's always possible to find such an answer. Now what about the case where a is odd? A equal to 5. In this case, 1, 2, 3, 4, 5 are the vertices. We start with a complete graph, and it has again a minus 1/2 edges. Again, let's call it ma, and we need to add n minus ma edges. If n minus ma is equal to 0, everything is fine. If n minus ma is equal to 1, then it's impossible. This is obvious because we need to add one edge to a complete graph. There are no options like in this case, where we could go back, not to do this step, but check how it can be done in a better way. Here we just have a complete graph. We need to add one edge. Initially, each vertex in this graph has an even degree, so both of these conditions are already satisfied. We just need to add edges in such a way that the degrees will remain even, but we need to add one edge, and that would make 2 degrees with odd degrees, 2 vertices with odd degrees, so it is impossible. So n minus ma doesn't equal 1. So n isn't a minus 1 divided by 2 plus 1. And if this condition is possible to just make a cycle with this many edges. It doesn't have to be a simple cycle. We can just make it in some way, either between, if this is even, then between vertices 1 and 2, and if it's odd, then between vertices 1 and 2, and then, or with 1, 2, 3, then back to 1. Of course, self loops are not allowed, so we need at least 3 vertices for that. Anyway, it's simple to construct the graph in this case, so we just need to remember that this works if a is greater or equal to 3. And if a is equal to 1, then of course we only have one color, so the cycle can't have any edges. That's a trivial case, and when a is equal to 2, then we have two colors and they have to be alternating on the cycle, so the cycle needs to have n even. It's only possible to use a equal to 2 if n is even, and that case is also trivial. So what's the time complexity of this approach? Of course, since we have conditions for what a is optimal, we can just try all possible a from 1 to square root of n approximately, or just up to n, it doesn't matter at all. The time complexity of that is just O(n). We check which is the largest a which satisfies these conditions, and then for that a we use the described ways to construct the correct complete graph plus some edges. Then we have a graph with n vertices and n edges, and we just find an Eulerian cycle in that. There are some standard algorithms for finding an Eulerian cycle, and the simplest one is just doing a DFS, and storing traverse edges in some stack, remembering never to pass through the same edge twice. So if an edge is in the stack, then we never pass through it. And when we go back through some edge, then we decide that this edge should be in the Eulerian circuit, and delete the edge. This is an algorithm for which it's not obvious why it works, but it's very simple to write. I use it, I found it somewhere, and it's very nice, even though I don't even remember why exactly it works. It's, as I said, it's quite complicated to figure out why, but you can think about it. It's also a standard algorithm. Well, it's simple enough to remember, but you can also just copy paste it if you don't know why it works. Now I will give you a link to this full editorial, just so you could have time to remember it, or you can look up the group in Codeforce's ASC editorial writers, and this is ASC 37, so it's somewhere near the top. So this is codeforces.com group /Q01CAL VL, I think, or it's IVI. No, it's IVI. Uppercase I, V uppercase I. Slash block slash entry slash 843 or ASC37. I made some detailed explanations of that contest some 2 years ago, 2 or 3 years, whatever. Another nice problem there is persistent queue, especially nice in that right at the beginning we should use some trick. We have a queue to which where we keep a copy of this queue at each moment in time after each operation we make on it, and we take this copy of the queue or the queue at this point in time and add or remove a number from it. So the trick we use is that for each vertex of the queue, we say that this vertex is for each queue at any number in time, we say that this queue is a vertex of a graph. The initial queue, which is empty, the initial empty queue is the root of the graph, and whenever we make an operation on the queue which creates a new queue, that new queue will be the son of the queue from which we did the operation. So for example, if we are pushing number 1, then in this vertex it will be the queue equal to number 1, and if we were pushing number 2, then we would have 1, 2. If we wanted to pop, each operation on the queue is either push number or pop last number. So here we would have a queue equal to 2 because it's a queue, not a stack, and we always want the last number. For example, we could have pop from this, so we would have a new vertex where the queue would be empty, and so on. Is always a 3, and like this we can just remember what operations were made on each copy of the queue without remembering exactly how each copy of the queue looked, which numbers it contained explicitly. But we can just implicitly get it by going from the root of the tree to a vertex which corresponds to the specific copy of the queue. And what we want to find is what number was popped from the queue for each pop operation. Since it's a queue, it doesn't matter in which order the pop operations were made, because whenever we pop a number, we have it guaranteed in this problem that we will never try to pop a number from an empty queue. This would be an error and undefined operation. So when we pop numbers, we remember that just into this queue in some order, in the order in which we have push operations from the root to a given vertex, and then we pop the numbers from this queue in the order in which they were given, in the order in which they were put into the queue. So if there are k-pop operations on the path from the root to our chosen vertex, then we pop k numbers at the end. The popped k numbers are the top k push numbers, so we need to find the k plus 1 or the k push number if the last operation is pop. For this vertex, for this copy of the queue, the last operation was pop, and so we need to find either what's if we only take k pops on the path to the top vertex of this pop edge, and find what's the k plus 1 on this path, or we take plus 1 pop operation and take the k plus 1 and take the k number that was popped that was pushed on this path. This is the same thing because if we take this longer path, then we just increase k by 1, and the number on this path which is popped is still the same. And this can be done again using some very similar ideas to LCA, just like I showed for the problem with the minimum spanning tree minus 2 times the longest edge of the spanning tree. It's basically the same. You just remember some properties of this tree at distance 2 power 0, 2 power 1, 2 power 2, up to 2 power large number, for example 2 power 17 or 2 power 19, and use that to find the kth number which is pushed on some path. For example, instead of finding the kth number from the top, we can just remember for each vertex of this tree how many numbers were pushed into the queue up to that vertex, ignoring the pops, and then instead of finding some number from the top, we can just find which number was pushed from the bottom. We can remember for each edge whether there was a push number, and we want the some kth edge from the top that has a push number, and then we just want to find out what's that push number when we know the edge. And we need also to remember in which order on the input the pops were made, so that we could order them in the right way and print them in the right order. And this would be O n log n. The most annoying problem in this contest was most likely problem I. It was geometry, of course, and some quite complicated geometry, but fortunately with a very low limit. So we have n obstacles. Each obstacle is a segment between point x1i, y1i and x2i, y2i, where I goes up to n, and n is up to 8. 8 is a very low limit, fortunately, and it allows us to do some sufficiently simple tricks in this. So anyway, each obstacle is a segment. There are various segments that don't intersect. So for example, like this, you would have 3 obstacles, 3 segments, and now Alice and Bob are playing a game on this plane. Alice wants to select some point that doesn't belong to an obstacle. For example, this point would be good. And this is Alice's point, and then Bob selects some other point. He can select an arbitrary point that also doesn't belong to an obstacle. For example, this can be Bob's point, or this can be Bob's point. And now Alice shoots at Bob. So we make a segment between points A and B, like this. And Bob wants to choose Bob wants to choose his point in such a way that the number of obstacles which Alice has to shoot through, or in other words, the number of segments that this segment between points A and B intersects. An intersection is also counted if they only touch. If these segments only touch at one of their endpoints, and Bob wants to choose his point in such a way that this number of intersected segments is maximum possible. But since Bob chooses his point after Alice, then Alice has to choose. We want to find out what's the optimal point for Alice. Alice wants to choose her point in such a way that regardless of which point Bob chooses, the number of obstacles which she has to shoot through is minimum possible. So Bob maximizes the number, Alice minimizes that number, and we want to find out what's the minimum number for Alice, and also one point which Alice should choose. If there are multiple such points, there most likely will be multiple such points, then Alice wants to choose any one of them. So this is quite complicated in that there are 2 points that can be chosen almost in any way on a 2-dimensional plane. They can have any real coordinates, and it's hard to figure out how that space of possible points should be limited. But it seems there, from how this problem looks, there should be some areas in the plane such that whatever point Alice chooses in some area, then the answer, the optimal answer for Bob will be the same. For example, in this case, if Alice chooses a point which is, okay, I'll delete this. If Alice chooses a point which is somewhere in this part of the plane, so at this side of this point, of this segment, at this side of this segment, then Bob will always be able to choose some point either here or here in such a way that it's hard to shoot through two. It's that Alice would have to shoot through at least one point. And for example, when we take the part of the plane that lies between these two lines, so the line crossing the endpoints of these two obstacles and the line crossing the endpoints of these two obstacles, then if Alice chooses a point in this area, for example here, then Bob can choose a point which lies in this area, which is on the other side of the two obstacles and also between these two lines. So Bob chooses a point like this. And that means Alice has to shoot through at least two obstacles. This actually tells us roughly what we should do. or how it works in this problem, that when we take two obstacles, we take two lines that pass through their endpoints. There are two ways to do that, but one of those ways only gives some weird areas, and well, we can separately deal with both those ways for each pair of obstacles. Then if Alice chooses a point which lies in this area, at one side of both those obstacles and between these two lines that pass through their endpoints, then Bob can always choose a point which is in the other side, which is at the other side, and make sure that Alice has to shoot through both these obstacles. Alright, how does it work next? And the solution I found before is that we are watching for the angles under which Alice sees some obstacles. For example, if Alice chooses some fixed point, then Bob's strategy is obvious. Just find out under which range of angles Alice sees each obstacle. So if Alice sees, for example, this obstacle under this range of angles and this obstacle under this range of angles, so from Alice's point there is an obstacle that covers this range of angles, and then there is an obstacle which covers this, then Bob should find some angle under which Alice sees him behind as many obstacles as possible, so some point which is covered by as many of these ranges of angles as possible. For example, here it would be 2, because there are 2 obstacles covering this range. And the question is how these ranges or their intersections change when Alice moves. The only way the optimal number for Bob can change in such a way that the ranges of angles under which she sees some obstacles become such that the endpoint of one such range is the same as the endpoint of another such range. So for example, here Alice would have to move in such a way that this endpoint that the endpoint of one obstacle is seen at the same angle as the endpoint of another obstacle. So in this case, this would happen for the angles under which Alice sees obstacles when she would move to this line. So from this point we will move to a point on this line. For example, if Alice was here, then she sees this obstacle under this range and this obstacle under this range of angles. So at this point Bob would be unable to hide behind both these obstacles at the same time, because their intersection would decrease when Alice would move beyond this line. When she is still on this line, since we count endpoints of obstacles as also parts of them, then the answer for a point on exactly this line would also be the same. But it is never optimal to stay on a line if we can move to one side and get a better answer, or get at least the same answer. So there are some special lines in that plane, and these lines are formed by when we have two obstacles. Then there are special lines formed by these lines connecting endpoints of different obstacles. We can find all these lines since there are just O(n) obstacles. Each obstacle has just two endpoints. Then there are O(n) squared lines. And these lines partition our space into a number of different polygons. If we could find all these polygons, then we know that the answer inside each polygon is the same, because the answer can only change when the sets of points, when the intersections of those ranges of angles, or the sets of points which have the same intersections of angles change, if one of those sets vanishes or appears. So for each of these polygons or infinite parts of planes into which the plane would be partitioned, we could just pick one point, since the answer for Bob doesn't depend on which point in that polygon Alice chooses. And for that point, we could just detect what are the ranges under which Alice sees the obstacles from that point, and find what's the optimal answer for Bob, and well, choose the point, choose Alice's point, which gave us the worst answer for Bob, so the best answer for Alice. How many polygons are there? Or what would be approximate to the time complexity of handling all these polygons and parts of planes? Well, the number of intersections between all these lines is the number of vertices of all these polygons. It's possible that some vertices are the same for multiple polygons, but there can't be too many polygons sharing one vertex, just O(n) squared again. And there most likely won't be. It's fairly hard to get the intersections when the points on the input have integer coordinates. Then it's fairly hard to get to make a case where there are many polygons which have many common vertices. So the number of common vertices is the number of vertices of all polygons altogether is O(n)(6) at worst, and the number of polygons should be something like O(n) to the power of 4 or something like that, but it doesn't matter. Even if we have O(n) to the power of 6 polygons and want to do an O(n) for each polygon and each segment, we do just a constant number of operations, so O(n) to the power of 7 times. In our algorithm, then n is up to 8, so 8 to the power of 7 is some, maybe a million, maybe a bit more, and that's completely fine. We can afford that without any trouble. So this problem was really just about finding some scheme in which we can solve it, or how to partition the plane in an optimal way, so that we could know that in each part of the plane into which it is partitioned, we would have the same answer. And then basically anything works. It's still complicated to implement because it's geometry and we need to detect polygons or polygons plus infinite parts of planes, which is still pretty tough to implement. but it's doable, even to this geometry. I'll mention that in the problem binary search, the solution is dynamic programming, but you can notice that in this problem, even though you are supposed to count the number of pairs of sequence and integer, which could be quite tough to do. So, which is quite a large number, and there is no modulo. You aren't supposed to solve this problem modulo anything, so you need to work with big integers. And actually, when you try it with Python, a language which naturally works with big integers, then you find out that these numbers can really get big. Here we have n up to 1000, and already for n equal to 100, the answer has some 100 or something like that. Yeah, it has about some hundreds of digits, so it's impossible to do without big integers. But on the other hand, and in this problem, you are only given one number on the input. So, for example, if you didn't want to submit a code which uses large integers and therefore can be too slow, also you can notice that we can't say that if the DP has some x state transitions, then the time complexity will be OX, because if the answer has ON digits, then each multiplication and summation and any operation takes ON time. So at least ON time for multiplication, for example, it will take longer. It's possible to do some fast multiplication using fast Fourier transform, but that's ON log n. And also a bad constant. So the time complexity, if without big integers, the time complexity would seem very, very good, suspiciously good. Then it's not so good because we still need to work with large integers. But on the other hand, n is only up to 1000. That n is the only number which is on the input, so we could possibly pre-compute the answers for each n. Let it run locally. For example, let it run in parallel. If you have a multi-threaded processor, then, for example, compute the answers for 8 numbers at the same time, and probably in several minutes, maybe tens of minutes. Even if you would get time limit exceeded if you submit it normally, then if you have a good computer and you go at it smart, you could just pre-compute all answers for all possible inputs. And
we tried doing that, but the numbers get so big that you can't submit the file because it has too many.
Really? Maybe you could just compute it for some, I don't know, the largest 100 numbers, and the rest of them most likely won't be in the test data. So that would be a smaller number of them to handle. And it passed, so it's possible to solve. The solution is dynamic programming, where each state only needs the size of the sequence n, and whether the first, without knowing this number x, because we want to find sequences such that when this binary search is run on these sequences, then it produces number x. Then it finds a number x, then without knowing what number x it should be, because x will just be the last number the bin search finds, so it doesn't really matter. And we just need 1, 0, minus 1. Each state only has n and one of these three numbers, which denote that the first number of this sequence a1 to a0 to n minus 1 is smaller than x, that a0 is equal to x, and that a0 is greater than x. This is O(n) states. So as I mentioned, there are O(n) states for n equal to 1000, but the answer can be big. Or possibly another approach would be to take just the top half or the top some number of integers from the answer, and then we would compute the answer modulo that number of remaining digits. So we would take some number of digits at the beginning of the result when we pre-compute it locally, then just hardwire those top something digits, and work with just less digits or a bounded number of digits with the resulting solution. In the solution we would submit. Anyway, these are quite complicated approaches, and they usually don't appear in real contests. So I just wanted to mention that there is this solution to B, which is dynamic programming on these states. You can think about how this dynamic programming works. Then there is a simpler dynamic programming problem, especially simpler in that we don't need to do these complicated things, and we can work modulo 10 power 9 plus 7 in this problem. It's problem F, permutations with monotonic segments, and it's about counting permutations for some sequence A1 through K. So permutations P1 through N for we want permutations exist for a sequence A1 through K, n is up to 300, and the sum of A1 plus A2 plus and so on plus AK is at most n is equal to n. And it gives us information about such permutations, that when we draw the segments of the permutations with lengths A1, A2, A3, and so on, number of elements are monotonic. So if we draw the numbers of the permutation in a two-dimensional plane, so at x equals y, we have y equal to pi. So points I, pi are drawn like this. Then, for example, if this was 1, 2, 3, 4, 5, 6, pi equal to 1, 2, 3, 4, 5, 6, then the monotonic segments of this permutation would have size 1, size 2, and size 3. A monotonic segment is a segment with maximum possible length, such that, okay, it's called monotonic, but it's decreasing. So a contiguous subsequence of this permutation, which is strictly decreasing and has a given length. The monotonic segments are disjoint. The number before the first number in any monotonic segment has to be smaller than the first number in the monotonic segment, or this number has to be at the beginning. Same for the last, which has to be either at the end or the number that appears after it must be larger. And we want to find for this given sequence, for this given length of monotonic segments, so A1 elements, A2 elements, A3 elements, and so on up to AK elements. We want to find what's the number of possible permutations P. The idea in here is that when we choose the numbers that should be in the last monotonic segment, or symmetric with the first, but simpler to work with the last, then we know in which order they go. If there are AK numbers in that segment, in the last monotonic segment, then there are n choose AK numbers we could choose. Or, of course, we need to watch out for what's the first number in that segment, because it matters for what can appear before it in the permutation. So if we choose this number, this first number of the monotonic segment number k, and this is equal to x, then there are x over x minus 1, because x cannot be counted in here, over x over ak minus 1, because we are choosing the remaining ak minus 1 numbers, ways to choose this remaining ak minus 1. Their order is uniquely given, so we don't do anything with the order. And then what we can do is just discard these AK numbers that were at the end and renumber everything in the remaining part of the permutation in monotonic segments 1 through k minus 1 in such a way that it would again be a permutation of numbers 1 through n minus AK. So from 1 to n we have a permutation of numbers up to n minus AK, but we still need some additional information, which is that when we do this, then if before the enumeration the number that appeared after the last number in the k minus 1 monotonic segment is x, then the last number of the k minus 1 monotonic segment must be at most x minus 1. And so we find which number is the largest number less than or equal to x minus 1, because some of those numbers can be in this segment, so we don't count those. So the largest number in here that's less than or equal to x minus 1, and then we find to which number it was remunerated. Let's call it, let's say that the last number is less than or equal to x prime. X prime is the number to which that largest one was remunerated. And we know that the last number of this renumerated permutation, renumbered permutation, must be less than or equal to x prime. If before the renumbering it had to be less than x. So less than or equal to x minus 1. And this tells us that the states of our dynamic programming should be n and this x prime, or the largest number, largest possible number that could appear at the end of a permutation. This gives us some more constraints on how we can choose the previous monotonic segments, how we can choose the numbers in them. And there is also a special case where if we have a monotonic segment with length 1, then we don't have two different numbers at the beginning, at the end, And okay, if we have multiple monotonic segments with length 1 is the same as having one monotonic segment that's increasing. And this works somewhat different, but it can all be handled. We need to pre-compute binomial coefficients for this. Of course, when we have pre-computing binomial coefficients is some O(n) squared algorithm. We also need to pre-compute their sums, their prefix sums. That's also O(n) squared. And when we handle all possible transitions from such a state to a next state, we have the maximum value for the last number. We need to choose the value of the first number of the last monotonic segment, and since we don't need to keep k as the number here, because as another number in these states, because k and x is just equivalent to kx, because the numbers n that we get afterwards are the same, are uniquely given by the sequence a. So from a state at the beginning n x prime, or n, because x prime at the beginning is n, we would get to n minus ak. We don't have a choice in to what states we move. When we know k, we know n, and since all ak are positive, then when we know k, we know how many numbers there are left in the permutation, so we know n. So these descriptions of states are equivalent. K is equivalent to n, so there are just O(n) squared states. And since for each state we need to try all possible choices of the first element in the last monotonic segment, then the time complexity of this is O(n) to the power of 3. This is the number of states is also the memory complexity, which could be kind of too big if we just wanted to remember O(n) to the power of 3 states, for example, here. But fortunately, we have just O(n) to the power of 2 states, and it's lightweight in memory. So we compute that modulo 10 power 9 plus 7. The other problems here are quite complicated. Which ones are left are blind flips, word cover, and that's it. For example, word cover uses suffix arrays. Suffix arrays are at the beginning suffix arrays, then there is some more stuff that's a KMP-like algorithm, and very often suffix arrays are paired with are paired with LCA or KMP, or they are used for transforming suffixes into just integers in some different order. Of course, a suffix array is just an array of suffixes of a string ordered in lexicographical order. So from string S1 to n, we get to an array of S. Is a permutation of suffixes. Each suffix and starts at some different index and goes up to Sn. they are ordered by in lexicographical order. So the first one is the empty suffix. It's always useful to have an empty suffix or consider an empty string to be a real string, because then, for example, when you compare or take some difference between